Tonight, we're going to explore something that most people never think about. When scientists talk about the observable universe, they're referring to a region of space that's roughly 93 billion light-years across. But here's the part that should make you pause. Just because we call it observable doesn't mean we've actually observed it. Not even close. By the end of this journey, you'll understand exactly how much we've missed and why most of the universe remains invisible to us. Before we go any further, if you find this exploration interesting, a quick like or subscribe really helps the channel grow. Now, let's dive in. When you look up at the night sky on a clear evening, far from city lights, how many stars do you think you can see? Under perfect conditions and with perfect eyesight, the human eye can see about 9,000 individual stars across the entire sky. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. That means you're seeing roughly 0.00002% of just our own galaxy stars. Now extend that thought. There are approximately 2 trillion galaxies in the observable universe, each containing billions, or even trillions, of stars. The total number of stars has been estimated at around 200 billion trillion, and we can see about 9,000 of them with our eyes. That gives you a sense of the scale we're dealing with. But things get even more interesting when we talk about galaxies specifically. While individual stars are too numerous to count, galaxies are the basic structures of the universe. They are the cities of stars, the building blocks of cosmic architecture. Here's where it gets strange. We know there are about 2 trillion galaxies out there based on careful observations and mathematical projections, but the number we've actually observed in detail is far smaller. As of 2025, the most comprehensive galaxy surveys have catalogued somewhere between 10 million and 50 million galaxies. Let's be generous and say 50 million. That's about 0.0025% of all galaxies. Put another way, for every galaxy we've observed in detail, there are roughly 40,000 we haven't looked at yet. If the universe were a library with 1 million books, we've read about 25 of them, and we're trying to understand the entire story based on those 25 books. So why is this the case? We have powerful telescopes. We've been studying astronomy for centuries. The answer comes down to a combination of time, technology, and sheer scale. Consider the size of the sky. The entire celestial sphere covers about 41,000 square degrees. Powerful telescopes like Hubble or James Webb don't look at the whole sky at once. They look at tiny patches. The famous Hubble Ultra Deep Field shows about 10,000 galaxies in an area covering roughly 113 million to the entire sky. If the entire sky were the size of the United States, the Hubble Ultra Deep Field would be about the size of a tennis court. And it took Hubble hundreds of hours of exposure time to capture that single image. This is the fundamental problem. To see faint, distant galaxies, you had to stare at one spot for a very long time. But the sky is enormous. There are millions of these patches, and we can only look at them one at a time. Second, there's the issue of technology and resolution. Not all observations are created equal. You can detect a galaxy, a faint smudge of light, but detecting it and observing it in detail are very different things. Detection might tell you a galaxy exists and roughly where it is. But to really understand that galaxy, its distance, composition, age, and structure, you need spectroscopy. And spectroscopy takes time. A lot of time. The Sloan Digital Sky Survey, which ran for years and produced one of the most comprehensive maps of galaxies ever made, obtained spectra for about 2 million galaxies. That sounds impressive until you remember there are 2 trillion galaxies total. That's 0.1%, 1/10 of 1%. Most of what we count as observed galaxies are photometric detections. Broad images where we know something is there and can estimate brightness and color, but we don't have detailed information. Think of it like this. Photometric detection is like flying over cities at night and seeing lights. You know a city is there. You can guess how big it is, but you don't know the buildings, the language, the culture, or how the city works. Spectroscopy is landing, walking around, and studying the city in detail. And we've only done that for about 2 million cities out of 2 trillion. Third, there's the issue of distance and faintness. The universe is expanding. Light from distant galaxies gets stretched as it travels, a phenomenon called redshift. The farther away a galaxy is, the more its light shifts into longer wavelengths. Eventually, that light moves into the infrared, where optical telescopes can't see it at all. That's why we need infrared telescopes like James Webb. Even then, the light is incredibly faint, sometimes just a handful of photons reaching our detectors. Detecting it requires long exposures and extremely sensitive instruments. Now let's clarify what we mean by the observable universe. This term confuses people. It doesn't mean the part we've observed. It means the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. But because space has been expanding while that light was traveling, the edge of the observable universe is about 46.5 billion light-years away in every direction, making it 93 billion light-years across. Everything within this sphere is potentially observable. The light exists. We just haven't captured most of it yet. That's what I mean by the invisible universe. It's not mysterious or unreachable. It's simply unseen so far. In 2025, astronomers using James Webb announced the discovery of over 1,700 groups of small galaxies in the early universe, less than a billion years after the Big Bang. Before Webb, we didn't know these galaxies existed. Their light had been traveling for over 13 billion years, passing the Earth while humans evolved and built civilizations. We just didn't have the right telescope pointed in the right direction. These discoveries revealed something surprising. Small, faint galaxies may have played a major role in reionizing the universe. Before this, scientists thought large galaxies were responsible. This shows that what we haven't seen isn't just more of the same. It contains surprises that challenge our understanding. And this has been the story of astronomy from the beginning. In the early 1900s, we didn't even know galaxies beyond our own existed. By the 1950s, we had catalogs of thousands. By the 1990s, digital detectors revolutionized astronomy. In 2016, galaxy estimates jumped from 200 billion to 2 trillion because we realized how much we were missing. James Webb, Euclid, Roman, and future telescopes will reveal more. But even then, we'll still observe only a small fraction of what exists. The fundamental limitation is time. There are only so many telescopes, only so many hours in a year. Observing the entire sky at the depth of the Hubble Ultra-Deep Field would take about 300,000 years with a single telescope. Add light pollution, dust, cosmic rays, detector noise, and data processing limits, and the challenge becomes enormous. Selection effects bias what we see. Bright galaxies are easier to detect than faint ones. Large galaxies are easier than small ones. This means our observations are skewed. So we rely on statistics to infer what we can't directly observe. That leads to a philosophical question. If we can never observe most of the universe, does it matter? I think it does, because it keeps us humble. It reminds us that despite all our knowledge, most of reality lies beyond our reach, for now. It also matters for life in the universe. If we've examined only 0.0025% of galaxies, then our failure to find life doesn't mean much. Every galaxy contains billions of stars. Every star may host planets. The invisible universe likely contains countless habitable worlds and perhaps civilizations. We're not running out of places to look. We're just getting started. The invisible universe isn't empty. It's full of galaxies waiting to be catalogued, stars waiting to be studied, and mysteries waiting to be uncovered. And that's what makes this the most exciting time to be alive and looking up at the night sky. And because these galaxies exist in regions of space we don't often survey, many of them remain undiscovered. The invisible universe includes these lonely galaxies drifting through cosmic voids. Then there are galaxies hidden by dust, either dust within our own galaxy or dust in other galaxies lying between us and them. The zone of avoidance, the region of sky blocked by the Milky Way's disk, is estimated to contain around 100 million galaxies that we can't observe at optical wavelengths. We can detect some of them using infrared or radio observations, but many remain invisible. Similarly, if a dusty galaxy lies between us and a more distant one, the foreground galaxy can block our view of the background galaxy. This process is called obscuration, and it's another reason large portions of the universe remain unseen. Now let's talk about the expansion of the observable universe and how it affects what we can see. Earlier, I mentioned that the observable universe is about 93 billion light-years across, even though the universe is only 13.8 billion years old. At first glance, this sounds like a contradiction. How can we see light from objects that are 93 billion light-years away if light has only been traveling for 13.8 billion years? The answer is that space itself has been expanding while the light was traveling. When light left a distant galaxy 13 billion years ago, that galaxy was much closer to us, perhaps only a few billion light-years away. But while the light was on its journey, space expanded, carrying the galaxy farther and farther away. By the time that light reaches us, the galaxy is now about 46 billion light-years away. And because space expands in all directions, there are galaxies just as far away in the opposite direction, making the observable universe 93 billion light-years across. This expansion has another important effect. It stretches light as it travels. This is called redshift. Light from a galaxy moving away from us due to cosmic expansion gets stretched to longer wavelengths. Ultraviolet light can shift into the visible range. Visible light can shift into the infrared. The farther away a galaxy is, the faster it's receding, and the more extreme this redshift becomes. For the most distant galaxies, those observed by the James Webb Space Telescope, the redshift is so extreme that light originally emitted as ultraviolet now arrives as deep infrared. That's why infrared telescopes like Webb are essential for studying the early universe. These galaxies are receding so fast that their light has completely shifted out of the visible range. But redshift does more than change wavelength. It also reduces energy. The energy of light depends on its wavelength. When light is redshifted, its energy decreases. A photon that leaves a galaxy as high-energy ultraviolet light arrives at Earth as low-energy infrared light. This makes distant galaxies appear dimmer than they would in a non-expanding universe. Combined with a normal dimming caused by distance, this makes extremely distant galaxies incredibly faint. They are emitting plenty of light in their own reference frame. But by the time that light reaches us, it has been stretched, diluted, and weakened so much that detecting it requires our most sensitive instruments. This is another major reason why so much of the universe remains invisible. There's also the issue of cosmic variance. When we observe a small patch of sky, we're seeing just one specific region. But the universe isn't perfectly uniform. Some regions contain many galaxies. Others contain very few. If we only observe small areas, we may get a misleading picture. Imagine trying to understand Earth's geography by examining a single square kilometer. If that square happened to be ocean, you'd conclude Earth is mostly water. If it were desert, you'd think Earth is barren. To understand a planet, you need to sample many locations. The same is true for the universe. To understand the full diversity of galaxies and cosmic structures, we need to observe large volumes of space. But here's the trade-off. The deeper we look, the smaller the area we can survey in detail. We can look deep, or we can look wide, but it's extremely difficult to do both. The Hubble Ultra Deep Field looked incredibly deep, revealing galaxies from the universe's earliest epochs, but it covered a tiny patch of sky. The Sloan Digital Sky Survey covered about 1/3 of the sky, but it didn't go nearly as deep and missed faint, distant galaxies. Ideally, we'd survey the entire sky at the depth of the Hubble Ultra Deep Field. But with current technology, that would take thousands of years. So astronomers are forced to make choices, study a few regions in great detail, or study large areas more shallowly. Both approaches are valuable, but both leave parts of the invisible universe unseen. Let me give you a recent example of how much we're missing. In 2023, astronomers announced the discovery of a massive galaxy cluster called El Gordo, Spanish for the Fat One. This cluster lies about 7 billion light-years away and contains thousands of galaxies. It's one of the most massive clusters ever discovered. What's interesting is how it was found. El Gordo wasn't discovered through traditional optical surveys. Instead, it was detected through a defect on the cosmic microwave background, the faint radiation left over from the Big Bang. Hot gas in the cluster scatters this background radiation, creating a subtle signal astronomers can detect. This technique is known as the Sunyaev-Zeldovich effect. Only after detecting this signal did astronomers use optical telescopes to confirm the cluster. This shows how observing the universe at different wavelengths reveals structures that might otherwise remain invisible. There's also the issue of time. When we observe distant galaxies, we're seeing them as they were billions of years ago. A galaxy 10 billion light-years away appears exactly as it was 10 billion years in the past. That galaxy has continued evolving, forming stars, merging with others, changing shape, but we can't see any of that yet. In this sense, the present-day universe beyond our immediate neighborhood is invisible to us. We only see the past. When we map the universe, we're not creating a picture of how it looks now. We're creating a composite image of different epochs. Nearby galaxies appear as they are today. Distant galaxies appear as they were billions of years ago. It's like a family photo album where each person's picture comes from a different year. The album doesn't show the family as it exists now. It shows a mix of times. That's what our maps of the universe are. The true present state of the entire universe is fundamentally invisible to us because light hasn't had time to deliver that information yet. Now let's briefly address dark matter and dark energy. Dark matter makes up about 27% of the universe's total energy content. Dark energy makes up about 68%. Normal matter, the stuff that forms stars, planets, and life, accounts for only 5%. Dark matter doesn't emit, absorb, or reflect light. Dark energy is even more mysterious. Together, they make 95% of the universe invisible to our telescopes. But for this discussion, we're focusing on the invisible universe made of normal matter, galaxies and stars that emit light but remain unseen simply because we haven't observed them yet. Even within that 5%, we've only explored a tiny fraction. And that brings us to the search for extraterrestrial life. If there are 2 trillion galaxies and we studied only a few million in any detail, then we've barely begun looking for life. Every galaxy contains billions of stars. Most stars are planets. Even if life is rare, the numbers are overwhelming. The invisible universe almost certainly contains life, perhaps even intelligent civilizations. We just haven't looked in enough places, at enough wavelengths, or for long enough. This is why exploring the invisible universe matters. It changes our perspective. It reminds us how little we truly know. And it shows us that discovery isn't slowing down. We're only getting started. But that remain unseen because we haven't conducted deep enough surveys of those specific distances. Now let's discuss the Milky Way zone of avoidance in more detail. Our own galaxy is a disk of stars, gas, and dust, about 100,000 light-years across and only about 1,000 light-years thick in most places. We're located within this disk about 26,000 light-years from the center. When we look toward the galactic center or along the plane of the disk, we're looking through enormous amounts of dust. This dust absorbs and scatters light, particularly blue and ultraviolet light. It's like trying to see through a thick fog. You can't see far, and everything looks dimmer and redder than it actually is. This creates what astronomers call the zone of avoidance, a band around the sky where we can't see distant galaxies at optical wavelengths. The zone is roughly 20 degrees wide, centered on the galactic plane. That might not sound like much, but it covers about 10% of the entire sky. Within this zone are an estimated 100 million to several hundred million galaxies that we can't observe optically. We can detect some of them at infrared or radio wavelengths, because those wavelengths penetrate dust better than visible light. But infrared and radio surveys don't yet have the same depth and resolution as optical surveys. As a result, most of these galaxies remain poorly studied or completely invisible. This has real consequences. There could be large galaxy clusters hidden behind the Milky Way. There could be nearby galaxies we don't even know about. In fact, astronomers have already discovered several relatively nearby galaxies hidden in the zone of avoidance using radio and infrared observations. In 1994, astronomers discovered Dwindlu 1, a spiral galaxy only 10 million light-years away, closer than many well-known galaxies. It had been hidden by Milky Way dust for decades. If we're still finding galaxies this close that were hidden by our own galaxy, imagine what we're missing at greater distances. The invisible universe includes everything behind the zone of avoidance. It's not invisible in principle. It's invisible because we're observing from inside a dusty galaxy. From a vantage point outside the Milky Way, these galaxies would be perfectly visible, but we're stuck inside. And until we develop better techniques for seeing through dust, or place telescopes far from the galactic plane, this portion of the universe remains hidden. Now let's talk about quasars and how they relate to the invisible universe. Quasars are extremely luminous objects powered by supermassive black holes at the centers of galaxies. Gas falling into the black hole heats up and emits enormous amounts of light, sometimes outshining the entire galaxy. Quasars were discovered in the 1960s, and for a while they were deeply mysterious. Today, we understand that quasars represent a phase in galaxy evolution. When a galaxy has plenty of gas available to feed its central black hole, it becomes a quasar. When the gas supply runs out, the quasar fades, leaving behind a normal galaxy containing a dormant supermassive black hole. Quasars are especially useful for studying the invisible universe because they are so bright. We can detect quasars at distances far beyond where we can detect normal galaxies. The most distant quasars we've observed come from when the universe was less than 1 billion years old, over 13 billion years ago. These objects tell us that supermassive black holes, millions or even billions of times the mass of the Sun, already existed very early in cosmic history. That's surprising, because we still don't fully understand how black holes can grow so large so quickly. But here's the catch. For every quasar we detect, there are likely hundreds or thousands of normal galaxies at the same distance that we can't see because they aren't bright enough. The quasar is like a lighthouse, brilliant and easy to spot. Normal galaxies are like small boats with dim lanterns, nearly invisible against the dark ocean. As a result, quasars give us a biased view of the early universe. We see the most extreme, most active galaxies, while missing the vast majority, the normal galaxies quietly forming stars without feeding an active black hole. The invisible universe at high redshift is dominated by these normal galaxies. We know they must exist because we see their descendants in the nearby universe. But detecting them directly is incredibly difficult. James Webb is beginning to find some of these normal high redshift galaxies, but even Webb can only scratch the surface. Now let's talk about gravitational lensing and how it helps us see parts of the invisible universe. Gravitational lensing occurs when a massive object, like a galaxy cluster, bends the path of light from a more distant object. This effect comes directly from general relativity, mass-warped space-time, and light follows that curved space-time. If a massive cluster sits between us and a distant galaxy, the cluster's gravity can magnify the background galaxy, making it appear brighter and larger. In some cases, lensing creates multiple images of the same galaxy or stretches it into long arcs. Astronomers use gravitational lensing as a natural telescope. The magnification can make a galaxy appear 10 or even 100 times brighter, bringing objects into view that would otherwise be invisible. This technique has revealed some of the faintest and most distant galaxies ever observed. But lensing is rare. You need a massive cluster in just the right position. Most distant galaxies aren't lensed, so they remain invisible. Projects like the Hubble Frontier Field program focus on 6 massive galaxy clusters, using their gravitational lensing power to search for faint background galaxies. These observations revealed hundreds of galaxies that would otherwise be undetectable. Still, this represents only a tiny fraction of what's out there. For every lensed galaxy we find, there are thousands of unlensed galaxies at similar distances that remain unseen. Now let's talk about the cosmic microwave background, or CMB, and what it tells us about the invisible universe. The CMB is the oldest light in the universe. It dates back to about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before this moment, the universe was opaque. Afterward, photons could travel freely. Those photons have been traveling ever since, and today we detect them as a faint microwave glow coming from all directions. The CMB shows us the universe before any galaxies existed. It's a snapshot of the infant universe, and it's remarkably smooth. Temperature variations are only about 1 part in 100,000. These tiny fluctuations were the seeds that eventually grew into galaxies, clusters, and the large-scale structure we see today. Satellites like Planck mapped the CMB across the entire sky with extraordinary precision. In a sense, the CMB is one of the few things we've observed completely. But that's the universe at 380,000 years old. The universe today, 13.8 billion years later, is vastly more complex. All the galaxies, filaments, and voids grew from those tiny fluctuations, and most of that structure remains unobserved. We've seen the seedlings. We're still mapping the forest. Now let's talk about cosmic noon, the period when the universe was about 3 to 6 billion years old. This was a peak era of star formation. Galaxies were forming stars at their highest rates. During cosmic noon, galaxies were vibrant and chaotic, forming hundreds or even thousands of solar masses of stars per year. Massive stars were common. Supernova explosions were frequent. The universe was brighter, bluer, and far more energetic than it is today. Most of the stars in the Milky Way were formed during this era. To understand our own origins, we need to understand galaxies at cosmic noon. But observing them is difficult. They are 7 to 10 billion light-years away, faint and hard to resolve. Surveys like candles have studied small regions in detail, revealing thousands of cosmic noon galaxies. But across the observable universe, there should be hundreds of billions. We're seeing only the biggest and brightest. The normal and dwarf galaxies from this crucial epoch remain largely invisible. Cosmic noon galaxies also look very different from modern ones. They were irregular, clumpy, and gas-rich, with star formation occurring in dense knots rather than orderly disks. Understanding how these chaotic systems evolve into the structured galaxies we see today is one of the biggest questions in galaxy evolution. Galaxy mergers play a major role in that transformation. Galaxies don't exist in isolation. They collide and merge. These mergers can trigger intense star formation, feed central black holes, and completely reshape galaxies. Two spirals merging can form an elliptical galaxy. Smaller galaxies can be torn apart, their stars scattered into halos and streams. The Milky Way itself contains evidence of past mergers in the form of stellar streams, remnants of dwarf galaxies absorbed long ago. We're also witnessing active mergers today, like the antennae galaxies and the mice galaxies. In about 4 to 5 billion years, the Milky Way and Andromeda will collide. The event will dramatically reshape both galaxies, though our solar system will likely survive. Detecting mergers at great distances is difficult. The structural disturbances are subtle and require high-resolution imaging. Many distant mergers remain invisible. To bridge this gap, astronomers rely on computer simulations. These simulations start with a tiny density fluctuation seen in the CMB and evolve them forward using the laws of physics. Projects like Illustris, Eagle, and TNG create virtual universes that closely resemble the real one. They predict around 2 trillion galaxies, including vast populations of faint dwarf galaxies that we've barely begun to detect. When simulations predict millions of objects and we've found only a few, we can be confident the rest exist. They are just part of the invisible universe. Finally, let's look to the future. The Nancy Grace Roman Space Telescope will survey huge areas of sky in infrared, detecting hundreds of millions of galaxies. On the ground, the Vera C. Rubin Observatory will photograph the entire visible sky every few nights as part of the Legacy Survey of Space and Time, LSST, cataloging billions of galaxies over a decade. These projects won't eliminate the invisible universe, but they'll shrink it dramatically. And that's the story of the invisible universe. Not empty, not unknowable, just waiting to be seen. Asteroids, supernovae, and many other transient objects will also be detected. The data from LSST will be a treasure trove for astronomers. LSST won't go as deep as Hubble or James Webb, but it will cover far more of the sky. It's a different approach, breadth versus depth, and it's complementary to deep, pencil beam surveys. The extremely large telescope, being built by the European Southern Observatory in Chile, will have a 39-meter, 128-foot primary mirror, making it the largest optical telescope ever constructed. The ELT will be able to study individual stars in distant galaxies, observe exoplanet atmospheres, and probe the early universe in unprecedented detail. It won't survey vast areas of sky like Roman or LSST, but it will provide extraordinary detail on carefully chosen targets. The ELT will help us understand galaxies we've already discovered in far greater depth, revealing their internal structures, stellar populations, and chemical compositions. The Square Kilometre Array, a next-generation radio telescope being built in Australia and South Africa, will be the most sensitive radio telescope ever created. The SKA will survey the sky at radio wavelengths, detecting neutral hydrogen gas in galaxies. Hydrogen is the most abundant element in the universe, and it emits a characteristic radio signal at 21 centimeters in wavelength. By mapping hydrogen, the SKA will trace the distribution of gas in galaxies, study galaxy rotation curves, and detect galaxies that may be too faint to observe optically but that contain large reservoirs of gas. The SKA will add an entirely new dimension to our maps of the universe, revealing the invisible fuel from which future generations of stars will form. All of these projects will help, but they won't eliminate the invisible universe. Even with every telescope working together, we'll still observe only a small fraction of the roughly 2 trillion galaxies that exist. We might go from 0.0025% to perhaps 1 or 2%. That's real progress. But 98 to 99% of galaxies will still remain unseen. The fundamental limitation is time. There are only so many hours in a night, so many nights in a year, and so many years in a mission lifetime. We can't observe everything. We have to make choices. And every choice means that some part of the universe remains unseen. This brings us to the philosophical implications of the invisible universe. What does it mean to live in a universe where most of what exists lies beyond our ability to observe? Does the invisible universe exist in the same way the observed universe does? From a scientific perspective, the answer is clear: yes. The galaxies we haven't observed are just as real as the ones we have. They are made of the same matter, governed by the same laws of physics. Their light is traveling through space right now. It exists, we simply haven't captured it yet. There's nothing mystical or ambiguous about the invisible universe. It's invisible only because we haven't looked yet, not because it's fundamentally unknowable. And yet, it's humbling. We're finite beings with finite resources trying to understand an effectively infinite cosmos. We'll never see everything. We'll never know everything. There will always be galaxies we haven't observed, stars we haven't studied, and planets we haven't discovered. The invisible universe is a permanent reminder of the limits of human knowledge. At the same time, it's deeply inspiring. The invisible universe represents an endless frontier. Every new observation has a potential to reveal something unexpected. We're not filling in the last missing details of a nearly complete picture. We're still in the early stages of mapping the cosmos. That's what keeps science exciting. Now let's bring this back to the human scale. Why should you care about the invisible universe? You're not an astronomer. You're not building telescopes, analyzing data. Why does it matter that we've only observed a tiny fraction of galaxies? It matters because it changes perspective. We live in an age where information feels abundant. With a quick search, it's easy to feel like we've figured most things out. The invisible universe reminds us that we haven't, not even close. Most of reality lies far beyond our everyday experience and far beyond our current ability to study. That realization should inspire both wonder and humility. Wonder at the sheer scale and richness of the cosmos. Humility at how little we actually know. When you look up at the night sky, you're seeing only a tiny fraction of what's out there. The invisible universe around you in every direction, vast beyond comprehension. It also matters for how we think about life in the universe. If we've observed only 0.0025% of galaxies, then we've barely begun searching for life. Every galaxy contains billions of stars. Every star may host planets. If life is even moderately common, the universe should be teeming with it. Our failure to find signs of life so far doesn't mean much. We simply haven't looked in enough places. The invisible universe almost certainly contains life, perhaps even intelligent civilizations. We just haven't found them yet. We're not running out of places to look. We're just getting started. Let's bring everything together. The observable universe is about 93 billion light-years across and contains roughly 2 trillion galaxies. These galaxies range from tiny dwarfs with millions of stars to giant ellipticals containing trillions. Altogether, the observable universe contains an estimated 200 billion trillion stars. And yet, we've observed in detail fewer than 50 million galaxies, about 0.0025% of the total. For every galaxy we've studied, there are roughly 40,000 we haven't. Most of these invisible galaxies are small, faint, distant, or hidden by dust. They include dwarf galaxies, low-surface brightness galaxies, galaxies hidden behind the Milky Way, early galaxies from cosmic dawn, normal galaxies outshone by quasars, merging galaxies too subtle to resolve, and stars drifting between galaxies in clusters. They are not invisible in principle. They are invisible because we haven't looked deeply enough, widely enough, or long enough. We're making progress. James Webb is revealing the early universe in extraordinary detail. Euclid is mapping billions of galaxies across vast regions of sky. Future missions like Roman, the ELT, and the SKA will push even further. Over the coming decades, we may increase the fraction of observed galaxies from 0.0025% to 1% or a few percent. But even then, most of the universe will remain unseen. That doesn't mean our efforts are futile. Every galaxy we observe teaches us something about cosmic history, dark matter, dark energy, and the evolution of structure. We don't need to observe everything to understand the universe, but we should remain humble about how much remains unexplored. So the next time you look up at the night sky, remember this. You're seeing a few thousand stars out of hundreds of billions in our galaxy. Beyond that are 2 trillion galaxies, most of which we've never studied. They're out there right now, shining in the darkness, waiting to be discovered. The invisible universe surrounds us, vast, humbling, and endlessly fascinating. Thank you for taking this journey through the invisible universe. If this exploration meant something to you, a like or subscribe helps keep these deep dives going. The universe is far larger than what we can see. Every time we look deeper, we find something new. And that's the beauty of it.